Okay. Okay, I think we can start with the introduction. Just 5 minutes late. So welcome everybody to the virtual seminars in complexity. This is the last seminar of the year and of the series that we had this year. But next year we'll be back. We still didn't set up the program, but we have already some speakers that are ready to start. Will be a slightly different format. We'll be inform you with our mailing list and on the website. So keep posted over the Christmas vacation. We'll try to set up the new program for the next year. And today we will have a single seminar, and it will be recorded, so you can listen to it later in case you have to leave. And it's posted on our YouTube channel. So like all the other seminars that you can find there that we had during this fall. The seminar will last 45 minutes and we'll have a discussion afterwards. Please use the chat to ask questions. We can also then do it live if you want, but please, just for organization reason, it's good to have the question in the chat. So today, we are very happy to have Ofer Lahav, who's the chair of astronomy at University College London, and is a great expert in observational cosmology, and in particular, he's an expert in dark matter. But today, and this is a bit the connection with our seminar series, which is mostly on complex systems and an interdisciplinary application of those. He will show us how to use artificial intelligence and machine learning to study galaxies. So this is, I think, a very interesting subject, and shows once more the possibilities that these new technologies offer to us in studying complex systems like the galaxy, which certainly is not simple. It's not a simple system. And the title of the talk is Darkness Visible, Complexity and AI in Cosmological Experiments. So without further ado, I leave the floor to Ofer Lahav.
Thank you very much, Stefano, for the kind invitation to speak to you. That's a kind of a challenge to speak to such a broad audience, especially when people are experts in this complexity issue. But I know there are also some cosmologists in the audience, for example, Gigi, who is an old friend. So indeed, as you say, it's complexity, and I think the letter D is missing in the title. It is about trying to connect these two disciplines. In fact, there is, of course, parallel activity in many other areas of connecting a traditional field with the new technology. Just because darkness appears here quite a lot, this is a map of dark matter. I'll show you some other versions later. This is from the Dark Energy Survey, in which we have been involved for many years, and this is using a technique called weak lensing, which results in a map of dark matter, if you believe all the assumptions, with the red spots are overdensities and blue are underdensities. And more locally, this is Andromeda and the Milky Way artist impression, which will collide one day. And again, I'll show you an example related to that. So, we'll talk about galaxy surveys, which have been a primary tool in our field for many years. I'll make some comments about the status of what's called the standard model, called dark matter plus cosmological constant. We'll talk then connected to the AI, and also I'd like to make some comments about the training of the next generation in this area, because the point is that our students have to be trained in a very different way to the way we were trained. Well, when I say we, I mean people in my age group. Maybe younger people have already been exposed to different ways of training. I should say this is a version, an upgraded version of a talk I gave at the Royal Astronomical Society George Darwin lecture in October, which was also for a broad audience. So I would like just to make a point straight away. I put AI in the title, and I'm sure most of you thought, well, that's artificial intelligence, but actually, I would like to make the point in this talk that maybe we should think a bit differently about it. And you may have heard some people advocate the concept of augmented intelligence. So it's also AI, but it's augmented intelligence. And I feel more and more inclined towards that, as opposed to the idea is, AI will do everything for you. You don't need students anymore. It would be AI. And even students write a thesis, well, it will be written by a robot. I think this is going too far. And I would say that we're in a situation here that we wish to connect laws of physics to human knowledge. We don't wish to throw away knowledge and intuition, and AI, which I refer to here as augmented intelligence. And we'll see some examples related to that. So where are we? We're in a very exciting time in our field that we have lots and lots of data. I mean, some of us may remember times where samples were very small. In my PhD, we use samples of thousands of galaxies. And now the whole community is basically flooded with data. And it's, this is Dark Energy Survey. This is not a project called DESI, LSST, Euclid SKA. Apologies for the acronyms. I'll come to them later. But you can see that we're talking about data which vary between 1 terabyte per night to 15 terabytes in terms of objects. We are now in the era of hundreds of millions, but it will reach soon billions. And the cost also goes up from tens of millions of dollars to billions, and also number of scientists goes up. We like to tell the funding agencies that it's actually a very good deal because it costs about only $1 per galaxy. So it's actually a very modest investment if you think of it this way. There are, of course, all kinds of sociological issues related to working in big collaborations. And those of you in particle physics, know a lot about it. In fact, we follow the footsteps of particle physics, of working in large teams. So these are some of these projects. I can just elaborate a little bit. So this is Dark Energy Survey, in which I myself been involved in now for 17 years or so. And this is the CCD of that telescope, which is mounted in Chile in a 4-meter telescope called the Blanco. And then on neighboring hill, if you visit the place, there's the kind of next generation, which is now being built. It's called LSST and renamed recently after Vera Rubin. At the same time, on a twin telescope of this one in Arizona, there's a project called DESI, which is a spectroscopic survey. It's a follow-up of earlier surveys such as BOSS. And Euclid, you probably have heard quite a lot about Euclid from Gigi, is an ESA project which involves both imaging and spectroscopy. Now, these are 4 out of many others. I'm just giving examples, visual examples, highlighting spectroscopy, imaging, ground, space, and also to say that there's a lot of effort in instrumentation. In fact, the optical corrector for both DES and DESI were built in our basement at UCL. So this is this Dark Energy Survey. It was one of the first, some people say the first, to actually simultaneously look at several different techniques, to look at the galaxy distribution and the large-scale structure of the distribution, to look at counts of clusters, to look at weak gravitational lensing, and also in the time domain to look at supernovae. And the survey strategy is, to have about 300 million galaxies. We already have it because the observation already finished, and thousands of supernovae, about 400 scientists, so it's still small relative to LHC, 400 scientists from 7 countries, and 6 seasons of observations were finished in 2019, over 250 papers, but we like to think the best is still to come, and the collaboration is working very hard these days about analyzing the data from the first 3 years and then from the first 6 years. Most of the cosmology results are only from the first year. So it's also an interesting lesson how long it takes from actually observations to actually producing papers. You know, it's quite interesting, you know, that it takes so long because of the complexity, right? It's a complexity because you have to take the raw data, simplify it, turn it into a catalog, and then it's the whole question of how do you actually analyze the data, what assumptions you make, and so on. We actually have some reflections on these projects we initiated, in fact, 7 years ago, when the observation started. We initiated a book which would tell the story, and fortunately, we're lucky that it's out. It's out there, and we had 2 virtual launch events, and you know, if people are interested in the, you know, the history of that project and also what the future is promising, you're welcome to look at it. It talks about the building of the project, the core science, but also some unexpected science. And there are also reflections by artists and anthropologists, a philosopher, and an artist. So, you know, we're trying to look at this in a more holistic way than normally is done in technical papers. Now, the core of this, many of those projects are actually driven by the quest for dark energy. And this is, I'll just remind you, Einstein in 1917, in this paper written in German, advocated this constant, which he called lambda, cosmological constant. Now, he put it there for a reason which he thought was important at the time, but he wanted to get a static universe. So he tuned it, it's a free parameter, he tuned it to give a static universe. Turned out the universe expanding, so he referred to his biggest mistake. It's a well-known story. What's interesting is that, you know, when I was a PhD student, lambda was believed to be absolutely 0. Okay, it would be a joke if you talked about non-zero lambda. And now this is the standard, right? So 70% of lambda or something similar to lambda, okay? There could be variations. And cold dark matter about 25% and 5% ordinary matter, baryonic. Okay, so this is the composition of the present universe, and this dark energy gives rise to an acceleration. In fact, technically speaking, what has been detected is acceleration. Dark energy is one possibility to explain it. A bit of history, when does it start? This is Einstein's equation. He put lambda on the left-hand side with the curvature, and these days, probably many theoreticians will put it on the right-hand side as vacuum energy. It's interesting, you take the weak limit, you get something which we're familiar with. Acceleration equals minus g over r squared, Newton's law, plus a linear force, which is repulsive. And a relatively little known fact is that actually Newton mentions a linear force as well in Principia, for reasons I don't have time to explain, but I can refer you to some literature on that. And Einstein put lambda in and out, and others like Eddington actually liked it. So you see, it has always been a very kind of elusive concept, and it's interesting that we happen to live now at a time that most people seem to like it. And this seems to be the standard. What happens is this lambda, you can think of it more generally, this dark energy is the equation of state, which is pressure over density. And you can work out kind of basic way, the density to be proportional to a to the minus 3, 1 plus w. And you can see easily when w is exactly minus 1, rho is a constant. So this is the case of a constant energy density, vacuum energy, and that's like lambda, basically behaves like lambda. If w is different from minus 1, you will have other behaviors. And the matter itself, of course, the density gets smaller. Here you have the redshift. So higher redshift is earlier time. And of course, the universe expands and the density gets more and more diluted, okay? the universe started accelerating about 6 years ago, and dark energy was sort of equal to matter at about 3.5 gigayears ago. How do we do it? We don't see lambda written on the sky, so that's an inverse problem, which many of you, I know, are working on in other contexts, that you have observables and you're trying to unfold the underlying physics there. And one possibility is to use standard candles that, if nature is kind enough, if the factory of nature produces exactly the same candles, you can tell distances by looking at the dimming of the objects. Or if nature is kind enough to put rulers for us, then we can place them at different distances, or they are in different distances, and we can tell the distances. So this is the basic paradigm in all this business of detecting dark energy. You know, if we find at the end that standard candles don't hold, then things can fall apart. So this is the standard. The rulers here, both in galaxy distribution and the cosmic microwave background. Weak lensing is another technique where light from distant sources get distorted, and the amount of distortion that you measure can tell you both about the growth of structure and the expansion of the universe. And then there are also classes of galaxies which you can count as a function of how many are there at different redshift, and this also tells you about both effects, the expansion of the universe and the growth of structure. Okay, so these are 4 of the most popular techniques. This is just, I hope it's going to work, a little animation that shows what happens as structure grows. Gravity is an unfair force. So the rich gets richer, the poor gets poorer. So regions which are a bit overdense will get denser. Now, a remark about complexity is that people understand how to run these simulations if you have only dark matter, but it's more tricky how to assign galaxies, because this has to do with the galaxy formation on very small scales. So that's this complexity of what to do on small scales. Is understanding of the galaxy formation good enough to then use this to derive cosmology? And some people like to they throw away information of small scales just because we don't understand it. So this is an example where there's room for understanding more complexity, testing it, so you can use it. Back to the cosmological constant, I already told you that most people think it's lambda. This is from samples of supernovae. So you plot the distance logarithmically against redshift, and this is a difference diagram, and you can see that there's a great fit to universe, which is about 0.3 in omega meter, 0.7 in lambda, and W is -1. And that's, on that end, the model, which was the standard model when I was a student, late 80s in Cambridge, but also elsewhere, was this model. Okay, so you can see how paradigm shifted, and this is another example of this W seems to be centered -1, and omega m is about 0.3. So seems everyone is happy, but there is also some tension, okay? So it's not all perfect. This is from the year 1 of this. We are eagerly waiting for the analysis of year 3. And this used lots of galaxies, not the whole sample. It's a subset, 650,000 luminous red galaxies and 26 million galaxies with shape information. Now there is a catalog, a dense catalog. It's actually of 100 million, okay? But what you can see in this diagram is, in fact, that if you look at the results from DES in blue and the results from Planck, they're not in full harmony, okay? There is some discrepancy there, and the question is, what do you do about it? So this is so-called tension. This is in a parameter space of clumpiness against matter density. So then you have to start questions, do you combine them? Are you allowed to combine them and get the red? You have 2 mountains, you can end up in the valley. Well, there have been different techniques developed to quantify tension, and it's all done in a Bayesian framework. But what I would like to emphasize in the context of complexity is the problem is, we solve for about 6 parameters of the universe, but we have in this analysis about 20 nuisance parameters which are not the cosmology itself, but other things which we need to know about the nature of the objects. For example, how does light traces mass? It's called galaxy biasing. Or what is the intrinsic alignment of galaxies? Because this could affect the way we interpret lensing. So this is the complexity. We mix the parameters we want with a set of parameters we don't know what they are. And nevertheless, in this analysis, it seemed to give the result people like, but we'll see what year 3 gives and year 6, which will have much more data. Okay, I mentioned also this tension. There's also tension in the Hubble constant, that one group that looks at the stuff locally finds 74 in these historical units, kilometer per second per megaparsec. It's really units of time, 1/time. On the other, the Planck satellite, which looks at the early universe, gives a number smaller, and the tension is 4 sigma. So, do you lose sleep at night or not? It depends on the individual. Some people spend their time understanding this 4 sigma. Some people say it might go away. I'm just giving you my own picture of this. Other people may say something different. And of course, one would like some new methods, and one of them is what's called dark sirens. And one can get this H0 also by connecting, looking at the distance from gravitational wave event, like the binary neutron star, and at the same time knowing the redshift to that event. And in DES, we've been quite active with that, as well as other groups. One can also use a dark siren, where you don't know, say it's a black hole, you don't know, there's no optical flash associated with it, but statistically you can say maybe the black hole system is in 1 out of 77,000 galaxies, and you do it statistically, and that's what you see in that red probability distribution of against H0, okay? So the gray is what you get from that binary neutron star, which is a good event. We hope to have more. You can see Planck is narrow, very narrow. Also, the local distance scale is relatively narrow. At the moment, the gravitational wave is quite broad, so it is still friendly with both. And in October, they released more events and so on. Again, you can see the complexity here because you're dealing with very compact systems, and modeling them, of course, require very clever methods using GR and so on. And then turning it into cosmological probe requires this statistical problem. As I said, you don't quite know where the object is if it's a dark siren. Okay, so I've given you hopefully the flavor of what's going on in this field in terms of the wealth of data and the need for methods. So for example, I didn't tell you how do we measure distances to objects, right? If we have only imaging, right? You need a method. It doesn't come from free. And that's where AI, etc., is coming in, okay? Now, I think this AI appears to some as something new, but, actually, I think it's been around for quite a while. I got interested in it way back last century, in the early 90s, and so were others, but it was very much on the fringes. And now, of course, everywhere you have, groups that work on it and collaborations and so on. But I think there are questions, is it just a black box? Can you explain it or interpret it? How do you minimize biases due to incomplete training? Can we include prior physics? Can we learn new physics? Yeah. And all that we would like to, understand, to relate it to what I would call traditional methods. Some of my colleagues don't like to hear traditional. They think of Bayes as something new. It's not new at all. It's been around for a long time. And I think it's nice to connect AI to these techniques, because all this analysis I've shown you of cosmological parameters comes using Bayes' theorem. This is just, I do a bit of a publicity here to AI and not just the human brain. I promise this is not an animation. It's not an animation, but how many of you It's a static picture. How many of you can see 12 black dots at once? I haven't met anyone who could see 12 dots at once. So here is our limitation of our brain. So usually we hear, oh, we need AI because we'll have billion galaxies. But actually it's also because just looking at things by eye could be misleading. Okay, so we want that. At the same time, as I said before, I preach for augmented intelligence, so there is an interplay, okay? So if I have an algorithm that finds 12 points, I'll come back to the expert and say, could you see 12 points? And this is now a big area. I'm sure there are many practitioners in the audience. And unlike the way it was in the 90s, now there are packages which are free. For example, scikit-learn, TensorFlow, and they can do classification and clustering and regression and dimensionality reduction, etc., etc. Okay, and then there's obviously a range of topics which are relevant here, and one is classification. So you want something like a neural network where you feed in parameters of an object and it will tell you whether it's a star or a galaxy. You can classify supernova, light curves, you can do strong lensing and deep blending and so on. I'll talk a bit about photometric redshifts. That's an example where we thought we can actually use just colors of galaxies and derive the redshift by machine learning approach. You can calculate masses of galaxies and look for planets and gravitational waves. So I just show you it's a huge area. I mentioned, for my sins, I got interested in the 90s and we wrote this paper about classifying galaxies by eye. My UCL colleague, a particle physicist who co-directs with me now the Center for Doctoral Training, Nikos Konstantidis, he apparently in his parallel universe in particle physics used already neural nets in the 90s. So it's not that new, but now of course it's becoming very, very popular, and I'm sure you have the same students knock on your door and say, could you give me an AI problem to do and so on. Galaxy Zoo is an example of that. These were galaxies classified by eye, but one can easily show that you can train. That is this concept that you show this is galaxy is a particular type, and you train and then predict, and you can see you can easily achieve success rate well above 90%. This is this photometric redshift I talked about. So all you do, if you want to demystify AI, you can just say redshift is a function of those filters. So if I observe the sky in particular filters, in this case those 4, but if I put even the same spectrum at different redshifts, I'll see a different amount of flux. So you can see it's an inverse problem, right? I can tell for particular combination of fluxes what's the most probable redshift. So that's the way of thinking about it. If you do think of neural net, if you like that, you can put the magnitudes here and you get the redshift here. We did it a while ago, and there are now more and more sophisticated methods. But this requires a training set. It requires that for a subset the true redshift. If you don't know that, you can use what's called template methods, which is based on just comparing it with a few templates. They could be simulated or from data. This is actually a pair led by my student Sunil Mukesh, together with Will Hartley and Antonella Palmazzi and the rest of the Dark Energy Survey. It just appeared actually on the archive yesterday, I think. It's just there, and now we take another step and use machine learning, not just to tell the redshift, but also the stellar mass. Okay, because in the color information of the galaxies, you have also that information. So you can see here a joint distribution, redshift and stellar mass, and you can see that it's you get if you have a good training set, it's very narrow. This is the probability distribution function. If you have a poor data set for training, you might even get by modality. It all depends on that, but never mind, it seems to work, and the paper also presents a package that Mukesh has produced. Now, these were all, everything I showed so far is in the context of the old approach of machine learning, namely when you actually extract in advance some features. So you classify a galaxy, you say parameterize it, you need another pipeline software to parameterize it, say, as 10 numbers. And that's what you feed into a neural network, and you get a classification, say, in a supervised way. But what's the new kid on the block, it's not so new anymore, but it's deep learning. And here what you do, you show the full image, not just extracted features, but the full image of the object. So this has been a breakthrough. It seems very popular. I understand from computer scientists that it's not entirely clear why it's actually working so well. There's some heuristic explanations for that, but it seems to work. So if you like, you can think of deep learning as part of machine learning, which by itself is part of the bigger family of artificial intelligence and even bigger family of inference. It's interesting, I counted this is, last time I looked at it was in November, so maybe there have been a few more papers since, but it's interesting how the number of papers with deep learning Untitled doubled, almost kind of doubled itself. Maybe it reached some saturation, because if everyone says deep learning in the title, it's getting a bit boring, right? But it's interesting to see the sociology of that. But I have to say, students love it, okay? They find it's a lot of fun to feed in images and to let the computer make decisions. What is the trick, for those of you who have not come across it? The trick is to actually, instead of doing pre-processing, extracting features, is actually take the image and convolve it with filters that pick up different features. Okay, so the filters, in a way, do feature extraction, but it's all built in. And then you can tell if it's a bird or a sunset picture or a dog or a cat. Now, as they like to say in England, the proof of the pudding is in the eating. Does it actually work in real life? So here, a group, I'm not part of that, but it's a very nice work from mimicking the LSST simulation, where I showed you arcs around clusters. So here, using what's called gravitational lensing, okay, you get those circles and arcs, which are an optical illusion. It's just because a distant galaxy gets distorted by the intervening matter, okay? So typically these days, say with DES, there's a group of people looking at it, although now DES also has a pipeline which is automated. But with LSST, you know, you'll have probably 1 million strongly lensed galaxies out of 20 billion galaxies. And what do? You need methods, okay? You need, whether you want to call it AI or machine learning or statistical algorithm, doesn't matter. You need something clever to do it. And there's actually a paper that mapped all these possibilities, led by Metcalfe. And this method with deep learning seems to be one of the best, if not the best. And they used this deep learning, a version of it, which is called convolutional neural networks, and the completeness of 90% can be achieved. Okay, so I think we see the power of it. Of course, that's on simulated data, but people are applying it for real life. There's another problem, just, you know, I can only give a few examples in a talk like this, but there's another problem with projects like LSST. There are so many galaxies there that they start overlapping each other. Okay, you look so deep. So suddenly you see more objects, and now you want to know that this object here is not one, but it's actually made of two. So again, you can build some sort of algorithm described in this paper by different group, or these two authors actually. And at the end, based on some training, it could tell you that actually this is made of two separate objects. And you can see the necessity of that. Of course, it could be mistakes, okay? There's a probability that it gets it right, but also probability it gets it wrong. The other thing is really to use all these techniques, not just to classify. In a way, classification is very simple, but also to describe the distribution of galaxies. So now each dot in this diagram is a galaxy, or a mock galaxy, and it's just so much wealth of structure. But historically, the only thing most people use the 2-point correlation function as a measure. It's a very useful statistic pioneered by Jim Peebles, who won the Nobel Prize this year, previous year. You know, all that is great. All that is great. But you can have two distributions which look very different by eye, which will have the same 2-point correlation function. So here, another student who in fact just graduated, they started a postdoc in Warsaw, Krishna Naidu, used a well-known technique, but perhaps underexplored in astronomy, minimum spanning tree, and you can see you create different functions out of it, and now you can tell one distribution for another, okay? So you can imagine, you can generalize that as part of the family of AI. Now, the title is of the talk, Darkness Visible. You may know it comes from the poet Milton, John Milton, Darkness Visible, but that's really a plot I showed on the very first slide of trying to get the distribution of mass. So that's what's happening here using this technique, a technique which is attributed to Kaiser and Squires, actually, in this version, which takes you from the images, the distorted images, and does the inverse problem and tells you what's the mass between us and those images that got distorted, and gives you that map, okay? So, and then you can look and check if really these are clusters or voids and so on. And that's the latest. This is from, again, former student, but we still work together, and now Jeffrey, now postdoc in Paris. And this is, you're among the first to see, this is a preliminary map, still blinded, of the DES full footprint. However, what's happening here in that method, and also an earlier one we worked on with Nile and others, is actually again using deep learning. And you take a different approach now. You actually train, you show the computer hundreds of thousands of simulations, and it tells you how to go from the measurement, the observable, which is the distorted images, to the actual mass distribution, or the projected one. It's called kappa. Okay, so it's an inverse problem that this kappa, the mass distribution, gives distortion, and to do it, in traditional method, you can invert this matrix operation, or you can use now lots and lots of simulations that would just educate the algorithm how to go from distorted images to dark matter. So this is what is going on now, and we're quite encouraged by it. And that's maybe a similar one. I don't have to go through details, but this group in Zurich used the same, and they even claim they can get cosmological parameters better. Okay, so they tell the algorithm, you know, if you see this picture, the amount of dark matter is such and such, and so on. Okay, so you have mapping. Now you can see the complexity here, okay, because you have very detailed images, and you're only asking for few parameters, but you know, what information there is the one that gives you those parameters? Okay, that's the question. And I realize, Stefano, that time is getting short. I'll try to speed up a bit. I'll try to accelerate like the universe.
Don't worry, don't worry.
Yeah, I'll take a few more minutes. I'm nearly there. This is, I just want to show another example, which I find quite interesting, because it's not classification or just getting few parameters, it's actually understanding dynamics. And I already alluded to it in the first slide, that in fact, Milky Way and Andromeda are falling towards each other. I don't want to scare you, but at some point they will collide and probably form an elliptical galaxy. So the future is pretty gloomy or attractive, depends on point of view, but that's only will take billions of years from now. So historically, there was something called the timing argument, which worked out just two bodies. And we've generalized it to think of it more as an AI approach. That again, you take many, many pairs of galaxies. Initially, simulations gave us 30,000, now we have 2 million. And instead of just solving that simple equation, which I showed you earlier, we actually tell the algorithm, look, if you have this pair and you have these parameters associated with this pair, that's the mass. Okay, you supervise. And the latest version of it is work with a postdoc of mine, Pablo Lemos, and it's all done. I don't have to go through the details. The paper is out there. And we used 2 million pairs, and we tested it on 10,000 pairs. I hope you get the idea, right? You show for each pair, you know the true mass, but we know parameters of the system, the velocity, distance. Sometimes you can also use information about the environment, and you derive that information. And that's, if you like, a number to take home. We find that the mass of the Milky Way plus Andromeda is 4.6 10 to the 12 solar masses with error bars, but quite big, so 50% or so. And it's consistent with individual masses, but we still live in a galaxy and we don't know quite what its mass. Okay, and this is shown here. This is the mass of the Milky Way. This is Andromeda, and yes, this is our result, which does touch the other values in 1 sigma. But it would be nice to know what's the mass of our galaxy. So I show you, these are techniques which you can do them in a very naive way, or you can take now this approach of using simulations to teach about the cosmological, the physical parameters. So I'm about to finish, Stefano, just a couple of summary slides that I hope I've illustrated. That first, there's lots of data in cosmology. There'll be even more for the next generation. And really that maybe we should think not just about everything being robotic, but how to provide information which will be shared with the astronomer and the knowledge. And then in terms of training the next generation, we started UCL this program 4 years ago, funded by STFC, our research council. We have now 45 students in 4 cohorts, and they, 4 of them, I have the privilege to supervise, very good students, Konstantina and Ben and Sunil and Prab. And they spent 4 years and 6 months they actually spent in a company of their choice. So they're being prepared for a dual career. Okay, at the same time, they do a project in astronomy, but they also could do a project on, the marketing for a fashion retailer like ASOS, or something about, for the oil industry, or for the Economist magazine, or some work on COVID. Okay, they basically do many different things. And it's all, I think, an exciting program we have, and we hope to see it developing. We even have a spin-off starting that program with Jordan, where we've given a remote machine learning course to 46 students, by the way, 62% female. So you can see also what's the international language of machine learning. It's across different fields, and of course across many different cultures as well. So to summarize, cosmology is undergoing this industrial revolution, and it's both in the spatial and time domain. And the challenges are incomplete. We have to deal with incomplete training sets and augmentation. We have to deal with how to incorporate the physics. I mean, do you tell in advance some of the physics, or do you wish the algorithm to discover its own physics? These are very interesting questions. How to interpret algorithms, and also, and I was just at a workshop last week, a virtual workshop, of course, on benchmarking and how to upscale algorithms. So if your algorithms work very well on 1,000 objects, maybe on 1 million, but what if you have 1 billion? This may break down, okay? So it's called benchmarking, and there's already some activity in the Research Council towards that. And either way, I think it's a great way to train the next generation. Well, they need it. And, sometimes I find myself, I'm behind. They already know algorithms and techniques, state of the art. But still, because I think of the human connection, it's good that they understand, how do you get the mass of Milky Way and Andromeda only as a 2-body problem, right? So you need that human intervention. you need this knowledge. Or here is the spectrum of a galaxy, and I tell you the redshift. Why is this redshift so good? Oh, it's because of that filter. Because there's an astronomer who spent time thinking about it. So, it's time whether we'll get an entirely new knowledge, whether a new theory will be discovered by machine learning. I don't know, and partly it depends on on how kind nature is to give us a chance to discover new things. And I'll just to thank all my, this has been an effort of many years, mentors and collaborators and postdoc and PhD students. That's a picture from a conference we had in April 2019, but it seems like, billions of years ago, given at that time we could actually be all together in one room and talk to each other and so on. Well, we hope, we'll be back in that situation soon. But in the meantime, great to talk to you virtually. Thanks very much for listening. So that's it, Stefano. Thanks.
Thanks a lot, Ofer, for this very nice talk with a lot of ideas and food for thought. So I open the discussion, so you can either send a message to the chat or just pose a question. Okay, Gigi first, please go ahead.
Hey, Ofer, nice talk. Thank you for the nice overview. I have a very general question, which I think might be interesting for more people. The difficulty when you think about applying machine learning to your field is to understand where do you stop trusting the black box and how much of your specific knowledge you have to put in. You mentioned this already, but perhaps you can elaborate a bit more. I mean, clearly we cannot, at this point, we cannot hope to be able to write machine learning algorithms which are better than those that you find on the market, because those, I think, are the result of a lot of thinking and working specific for that. At the same time, as you said, you feel uncomfortable to use a black box, and understanding how much you have to provide of your own specific knowledge to the algorithm, where to stop. This is a bit my difficulty when I think about using this.
Yeah, so your point is exactly along the lines I was trying to convey, that I think there's a room to use this new machinery, but also to combine it with previous knowledge and maybe more traditional methods, not to throw them away. So I think some of it is just, about really, okay, you put something fancy, with all these hundreds of thousands of simulations, and you put deep learning and something comes out, the mass of the Milky Way and Andromeda comes out, but you can also, how to do it with pencil and paper, right? Do it with pencil and paper. So I think feeding in some simple cases, almost trivial case, it's a bit like, comparing numerical, when you do numerical work and you go back to a few analytic solutions. I feel a bit the same about that, to actually educate. So one thing is, if you like, is to just see, there are two concepts. There's something called explainability and interpretability, which are not quite the same. One is just you interpret the results. You know that if you put particular input, you'll get some output. But there's the deeper level of actually understanding what it does. Okay, so it seems to me the combination of simple cases to see what they give is one. Also, people have developed methods to look at the free parameters of the algorithm and analyze that. Okay, so although you have all these free parameter weights in the neural net, for example, or these parameters in these parameters in decision tree, you can actually analyze them and find that maybe out of these 100 free parameters, maybe only 20 are important, and the others are not. So I think this is actually a very important area and still needs to be explored. Yeah.
Thank you. Thanks.
So I have just a curiosity. So normally all these deep learning algorithms that are being used for images and so on, typically work on 2D images, no? Or at least that's my impression. So how does it work in your case? Do you feed them 2D data or 3D data?
A short answer, 2D, because that's what you see on the sky.
Okay.
So you just, all you request from it is to classify it on the sky, because that's the only way you see the galaxy. You can do something more sophisticated with use simulations of 3D and train on different projections, and maybe even do it inverse problem and discover what's a typical three-dimensional structure of what you see as 2D.
Okay.
In addition to that, by the way, now there's also dynamical information about galaxies, not just the image. So you can combine that as well and get some kind of the phase, well, not quite phase space, but both spatial and the velocity information.
Another way, I mean, independent from IE, for artificial intelligence to get the 3D coordinates of the galaxies. No, I guess there are some indirect ways, or is it something?
Well, you could do reconstruction. Of course, now there's this, for the Milky Way, there's all this Gaia data. There's a data release just the other week. But even for distant galaxies, you can do two things. You can just study only one galaxy and use dynamical information and modeling to figure out the 3D, or you can use maybe an ensemble of galaxies which you think belong to the same family by some criterion, and use that to reconstruct what it would look like if they're all more or less presenting a similar underlying 3D.
So other questions from the public? Okay, Davide Bianchi, please.
There we go. I offer thanks for the very nice talk. I have a very naive and, let's say, vague question, but maybe you have already thought about that. So in the example you have shown, basically you have inferred the mass from the distribution of galaxies. And to do that, you have trained your machine learning thing on simulations. So you have simulations which has all the physics inside to run, basically, to simulate the universe. So the way I see it, there are two things that you can do. One is to run totally unconstrained simulation and then use them to train your machine learning machine. And the other thing is to run constrained simulation and feed them to the data with some forward modeling, right? So
yeah.
Why is it more convenient to do machine learning, and what is the conceptual difference? I mean, you're always putting the physics in your simulation at some point. What is it in machine learning capture that you wouldn't capture with forward modeling? Of course, I presume it's faster, but other than that, is there something else?
Yeah, so first, I haven't explained, but with those 2 million simulations, it was done in a forward modeling. I mean, I can maybe don't take too much time on this, but it's the probability. You can see the probability for the parameter. In this case, it's the mass, given observables and some, hypothesis. So the way it's done, it's, if you like, you start with a very kind of clean sets of simulations, and then you put on them all the observational uncertainties, okay? So you create now an ensemble of 2 million pairs which have similar observational selection effects or systematics like we think are in the data. So now it's a question, so it does forward modeling actually, which is what you want, which is much easier to handle. But now the question is, what you want is, given many parameters, how do you decide given the observables of one system, how do you decide, how do you do the inference? Okay, so you can write, you can decide you just want to be Bayesian and put some analytic functions there. But the problem is that you need to write a probability distribution, and typically people put Gaussians, okay? But which is adequate in some cases, but it could be too naive in other cases. So this new field, this new approach called likelihood-free inference, LFI, and then you don't force any form. You actually, the whole ensemble of the simulation is your likelihood surface, okay? So it achieves both the form modeling and a free, well, I don't actually like the name likelihood free because there is likelihood there. It's just that you have to, you don't force it to have a particular form. Does it answer your question, Davide? Or?
Yeah, I would say, yeah.
Okay, okay, okay. Thank you.
Are there other questions? Lee, okay, there is a question in the chat. I'll read it. Thank you very much for the interesting talk from Linda Ravazzano. I have a naive curiosity from someone outside the field. All the measurement about dark matter rely on indirect methods, such as gravitational lensing based on gravity force. What if instead of hidden matter, there is something we don't understand yet in gravity, especially at large scales? Is this hypothesis diffused in the field?
Yeah, that's certainly a valid question. We work in a particular paradigm, which most people like at the moment, but not all, not everyone likes it. So, you know, I have a colleague, Moti Milgrom, who believes that dark matter in galaxies doesn't exist. It's really, we need to tweak Newton's law. So Milgrom, who works at the Weizmann Institute, he believes that, you know, you tweak Newton's law to something different, which then gets rid of dark matter. So it's a very nice idea, very interesting idea, but it also has some problems with certain systems. For example, there's a colliding cluster, something called the bullet cluster, which shows you that there is dark matter there. So it's, but people like him have been thinking about it, but actually the current surveys and also the next generation of surveys also look at models of modified gravity, because it's, you know, I mentioned Milgrom's MOND, it's called, is on galaxy scales, but people also look at very large scales, and then we don't know, we have not tested general relativity, so people allow some freedom in the analysis, and you'll see papers on present data, and you know, DES and so on, BOSS, that people look at that, but also quite a lot of feasibility studies for Euclid, LSST, to check the deviations from ordinary gravity. But it's probably fair to say that so far general relativity is doing pretty well. Of course, this also brings the question, when do you stop? When do you decide it's good enough? And this has to do with the error bars, right? So for one person being close to general relativity to 5% is good enough, and they say, let's move now to work on something different. And other people say, no, 5% is not good enough. We would like to see it at the sub% level, okay? There comes human judgment. When do you decide you sell your shares and you buy new shares, or you continue on and on and on until it's in the textbook below 1%? Well, you know, I know colleagues who, you know, on different camps. Yeah.
Okay, are there other questions from the audience, either in the chat or also live? We have many questions already. So if there are no questions, I think we want to thank very much Ofer for this very nice talk. And as I said, the virtual seminars on complexity will continue next year. We still don't have released the program, but it will come.
We have a program.
We have a program. We didn't release it because we are fixing the last details and title.
By the way.
And so you will find everything in our website and on Twitter. Follow us on Twitter, and you find all the talks. This is talk number 7, I think. Actually, we had 13 talks, because most of the time there were 2 speakers. So all these talks are available on YouTube, on the YouTube channel of the Center for Complexity of Biosystems of the University of Milan. So you are welcome to look at them if you missed some of them.
Yeah, and next year we will also have probably topics on sustainability, since this is also something that is related to everybody. So
we will also always try to alternate
and
different topics.
everybody wants to give a talk, to discuss what they are doing, what is his or her doing. Please
send us a message.
Yeah.
Okay.